Okay. So let us see what is the actual goal for this session, right, or for this analysis. So in this workshop, we will analyze the pump housing shown below for its heat transfer characteristics. So this is what actually a pump housing, right? So all of you will get the meaning of this, right? What is in the pump housing, right, and why it is used. So it is just a casing which is which covers the pump's assembly, right? So especially a plastic and aluminum version of the housings will be analyzed using the same boundary conditions. So we will see, we will take the two materials, one is a plastic and second is an aluminum, right? And we'll go, we'll try to find out the, we will try to complete the analysis on these two materials, right? Then our goal is to compare the thermal results for each configurations, right? Thermal results for the plastic material and thermal results for the aluminum, we can say material, right? So that is what the comparative study we have to do. And this is just one example, right? I will just explore here. Uh, as all of you are doing some projects on your topic that you have selected, right? So if your project is related to the FA, right? If your project is related to the analysis part, that is related to the ANSYS, you can do just like changing the material, you can do the comparative study also in your project. So that is also one topic of your study, right? Or we can say that is also a topic of your project also, right? So this is just here example is given, right? That is the pump housing is given, right? And just two materials are taken for study. One is plastic aluminum and second is aluminum, and their comparative studies are done here. You can see that. Okay, so steps are given here for the analysis. You can see that. So assumptions are made in this. The pump housing is mounted to a pump which is held at a constant 60 degrees Celsius, right, temperature. We assume the matting phase on this pump is also held at this temperature, right? So matting phase means these phases, right, of this pump. Might be, I think the arrow is visible with you in front of you, right, in the screen. So the interior surface of the pumps are held at a constant temperature of 90 degrees Celsius by the fluid. That means interior means this one, right? Interior faces of this. Okay, so here you can see the boundary conditions are shown here, right? Actually 60 degrees is given for what the matting faces, that means these faces, and the 90 degrees is given for the interior, that means this part. Okay, interior, it is 90 degree and this is for 60 degree. Okay, the exterior surfaces are modeled using a simplified convection correlation for tangent air at a 20 degrees Celsius. That means this exterior surfaces. Okay, so here the convection is considered and the temperature is considered as a 20 degrees Celsius. So these are the some assumptions, right? These are the three assumptions. You can say that for the interior temperature will be 90 degrees Celsius. The matting surfaces of that housing will be subjected to 60 degrees Celsius, and exterior surfaces will be subjected to a, we can say, 20 degrees Celsius. Okay. Then next, you can see how to do the analysis, right? The steps are given here. First, you have to select the units. We can select the units. It should be in metric, right? That is kg, mm, like that. Okay, second, Celsius, milliampere, millivolt, like that. Then next, display values in a project unit. That is, it should be, you have to just tick here, right? Then next, you have to select the type of module, right? What type of analysis you are going to do. That is, we are selecting the steady state thermal analysis because we are going to do the thermal analysis. So that's why we are selecting here a steady state thermal analysis. You can see just one numbering, one number is given to that. That means this is a step number one actually. So from the toolbox, double click the steady state thermal to create a new steady state thermal system. So we have to just double click, we'll get one a new system like this, okay, which consists of one steady state thermal analysis module. In that, again, the different steps are there, as like an static structure analysis, like that, engine data, geometry, model, setup, solution, and results. Okay, the next step is go for the geometry, right? Just right click of mouse button, right? The geometry, RMB stands for right click, right? Right of just you have to right click on this geometry, right cell, and just you have to import the geometry. So geometry you have to select as a pump housing .xt file. Okay, so you are directly importing the geometry. You can create the geometry also by clicking on new geometry tool, right? But the geometry is available with us, so we are just going for importing the geometry. The next step number 3 is that just go for the engine data. That means, can anyone tell me what are we are doing in the engine data, right? what is the use of this engine data tool or tab, in which what we are doing? We are doing the meshing, we are giving the boundary conditions, or we are finding the solutions, or any other. Engine data stands for what? Anyone can, yes, selection of material, correct, to Shitesh. In engine data, we are selecting the material, right? Now, remember that actually in the aim of this project, right, or aim of this analysis, we have seen that we are going to do the comparative study, right, for the plastic and aluminum version of the materials. So that means we are using two materials here, right? So that's why we have to select the two materials in this case. You can see that with general materials, just click on general materials, right? When we click on engine data, you will get new tab. In that tab you will get the general materials, so just click on that general materials, you will get another new tab. In that you will get the aluminum alloy. That is our one of the material for the analysis or for study. So just click on aluminum alloy, that is on plus sign. Here you will get the dictionary. You can say that the aluminum alloy material is added in our dictionary, right, or in our analysis. The next material, that is polyethylene, right? That is one type of plastic we have to select. So polyethylene material is selected. Again, just click on that plus sign. You will get that polyethylene material is also added in our library. So after that, you can just click on the return to the project, right? That is available at the top of the toolbox, right? So you just click on that, return to the project. You will get directed towards this window, that is in the project schematic. Okay, so here you can see that in the engineering data, there is a green color tick mark is there. That means you have selected the data. Then we have imported the geometry also, so that's why here we are getting an tick mark with a green color, right? Now next step is modeling, right? So in that model, we are going to do the meshings, we are going to apply the boundary conditions, we are going to solve the problems, and then we are going to find out the different parameters related to the thermal analysis, right? So these are the what we can say the steps to follow, right, for the next analysis part. So you can see here, right? Now here you can see. Can anyone tell me what is the actually 6 number step here? What is done in six step number 6? Can anyone tell me? Here also you can see. Now this is just what is this steady state thermal analysis. We have just copy here, right? Okay. Now we have got two steady state thermal analysis, A and B, right? Now we have just imported the material from A to B also, and we have imported the geometry from A to B also. Just click on 3A and just drop here in 3B, like that. Okay. So whatever the geometry available in the A module will be share with the module B also, and whatever the materials available with module A, that is also share with the module B, like that. Okay. Why we have done two modules here, different modules? Because we are going to see the comparative study, right? That is for polyethylene and for aluminum material. So that's why two modules we have taken here, right? Okay. Now next, double click on the model, right? Let's say for A. Okay, so model. Uh, then system opens the mechanical applications, right? In that you have to just select the unit as a metric, that is in mms. This should be in degrees, then the rpm, celsius, like that. Okay. The next here you will get the one we can say the two tree, right? So in that tree we'll get a model A4, right? Below that there will be a geometry, and there will be a part 1. Actually only a single part is there, so that's why here only part 1 is showing. It is not assembly of n number of components or 2 or 3 components, right? So if there is assembly of 2 or 3 components, you will get 2 or 3 parts here, but here only a single system is there, a single part is there, so only part 1 it is visible in front of you, right? So after that you can just click here, right, on that part 1, right? So when we click on that, here we will get the details of part 1, right? So in that window at the bottom you can see the material is there, right? So in the material you can go for the selection of the material, right? That is your B step, right? from the details import the material, that is polyethylene, right? So just you have to click here and you have to select the material. It might be by default it is a structural steel, but in library added the polyethylene and aluminum alloy, so we can select as a polyethylene, right? So polyethylene initially we are selecting as a material. Then next you can go for the mesh, right? At the bottom you can see here the meshing option is there. So select the mesh and go for the relevance as 100, right? We are going to do the fine meshing, so that's why we are selecting relevance as 100, right? So then next the steps are that apply the boundary conditions, right? That is step number 10. So how to apply these boundary conditions? You can see here the boundary conditions are applied with the help of these tools, right? Here in this you can see the steady state thermal, right? So in that, just when we click on that steady state thermal A5, you can apply the boundary conditions like temperature, convection, radiation, like that. Okay, so let us one by one we apply. So first select the interior surfaces, that is 13 faces are there of the pump housing. Interior face means this face, okay, that is shown in the green color with the notation A. Okay, so if we select these all faces, yeah, the count of that faces is actually 13. Okay, now after that right click on that and insert temperature, right? Because in the analysis goal, or the before the starting of this workshop, we are given, or we assume that the interior surfaces of these housings are subjected to a temperature of 90 degrees Celsius. Okay, so that's why we are setting here temperature as a 90 degrees Celsius. Then next the matting surface of these housings, right? That means these surfaces are subjected to a temperature of how much? It is 60 degrees Celsius. So just select these surfaces, right? Right click on that and insert again a temperature. It should be on 60 degrees Celsius again, right? So that is your DEF steps for the exterior part, right? The next go for the convection, that is exterior surface of this housing, right? So select the exterior surfaces, that is 32 surfaces are there, right? Of the pumps housing. Then again insert, right click just and insert, you'll get the convection option, so just click on that convection. Okay, then after that you can go for the import option. You will get two options, that is import with temperature, right, or import with data available, right? So you can go for the import with stagnant air, right? That is simplified case you have to select here. Okay, and after that you have to mention temperature as a 20 degrees Celsius, that is given in the problem, right? So just click here 20 degrees Celsius temperature. Then go for the solving problem. Just you have to click on the solve, that is step number 12. You can see here it is given in the image also. Now next, when the solution is complete, insert temperature and total heat flux results. So you have to go, select here the temperatures, right? And the total heat flux, so you'll get the temperature variation in that housing, and also you'll get the heat flux results for this housing. So this is what the final results, right, of the model A. Same for the model B, but you have to change the material in that. You have to take the aluminum alloy, right? And all results will be the same. You can just compare these results, aluminum alloy with the polyethylene material, right? You will get the difference between these. This is what the heat flux, right? Results of the heat flux, total heat flux. So this is the actually total actually we can say the steady state thermal analysis of a pump housing, right? Or the thermal analysis of the pump housing. So I will just now start the ANSYS toolbar, ANSYS window. Okay, and we can see this. We can do the analysis, right? Might be if the ANSYS software is available with you, right? That is in front of you, or it is in your laptop. Simultaneously, you try to do, right? But I think now the files and other things are not available with you. Just okay, you but just do the practice, right? When you will get the times. Meanwhile, we'll start the ANSYS. Just wait for a few minutes. Okay, so I think this is visible, right? This is in front of you. The ANSYS Workbench GUI, graphical user interface. So let's start with the analysis of this pump housing for thermal analysis part. Okay, so let's follow the steps what are given in this presentation, we can say, right? So initially, I will select the types of analysis as a steady state thermal analysis. So here you can see that there is option that steady state thermal analysis. So I will just select that. Okay. Then I will go for the engine data, right? So in that, I will try to add the materials, right? Whatever the materials we required. So I will just click here in the engine data source. So all of you are now aware about these steps, right? So in general materials, I will click on the general materials. I will try to add the aluminum alloy also, right? And another material is that polyethylene, right? So both these two materials, that is static structure, structural steel is by default available, but we have added the aluminum alloy and we have added the polyethylene also, right? So these two materials we added in, these are the two materials we require for the analysis. I will say that update project and I just click on the return to the project, right? So you may observe that here, right? All our question marks are there for the geometry model setup. But when we upload the engine data, right, you will get the tick marks here, right? Okay, and by default, there will be a tick mark for the engine data because by default the material is taken in that is structure still, right? So remember that. The next, let us try to add the geometry, right? All of you know that you have to just click on the right click on the geometry. You can create a geometry in the ANSYS itself also, or you may import the geometry, right? Okay, so the geometry of that pump housing is available with me, so I will just directly import that geometry. So I will click on import geometry and browse option. So here pump housing dot xt is available, so I will just click here. So you can see that again the geometry in front of geometry, the green tick mark is there, so it is added. Okay. Now, actually, we are here. You can rename that also, right? So let us say we are seeing for the aluminum, right? And next material we have added in the library is that what is that? Polyethylene, right? So we'll see for the polyethylene also. So I can here just make a right click here also, and I can just make the duplicate also, right? So it becomes what two files are generated for the steady state thermal A and B, right? I can just click here and drop here so that it, the meaning of this is that the material is selected here, right? Same material will be selected in this module, same geometry will be imported here, but I have made it as a duplicate, so I will just here mention as a polyethylene, right? Poly. So here actually okay. The next let's solve for the first aluminum and then we'll see for the polyethylene, right? So I will click on aluminum. I just click on aluminum, that is on the model. Okay, so you can see this is a geometry of pump housing right in front of you. Here the outline of the project is given, right? So let's see, let's try to add the material here. So geometry part one. In the material, you can see that here the by default it is structure steel, but I will select it as an aluminum alloy, right? So the material is selected as aluminum alloy. Then I will go for the meshing and I will set the relevance as 100. All of you know the meaning of relevance in the meshing, right? We have seen the experimentation on that in the previous project, right? So I will just right click here on the mesh and I will say generate mesh. So meshing will be done here, right? You can see here the meshing will be done, right? Now after that, you can follow the steps, right? Here it is given. Apply the boundary conditions, right? That is temperature, interior, then to the matting surfaces and exterior, right? So we will see if we will apply the boundary conditions now. Okay, so just click on steady state thermal. You will may observe this some environmental conditions are given for the steady state thermal analysis. So I will just click here, right? I will select the interior surfaces initially, right? And then I will see the to apply the boundary conditions. Okay, so how many faces are selected? You can see here the 7 faces are selected, right? And approximate surface area is also given. It is 8649.1 mm square. Okay, now actually interior surfaces means this one. Okay, then this one, then this one, this one. Just you have to press a control key, yeah? So that you can see select the number of faces. So now you may observe that here the 13 faces selected, right? So as we know that actually here, right? So 13 faces you have to select. Okay. Then after selection of these faces, you just right click here and you just mention that insert, right? So insert, you have to insert the temperature. Temperature how much? It is 90 degrees Celsius. And see 90 degrees Celsius temperature. Okay, so 90 degrees Celsius temperature you have to. The next is that the matting surfaces, right? The matting surfaces will be we can say this surface, right? Only. And again, right click on that. Insert temperature here. It is 60 degrees Celsius. Okay. So now the two boundary conditions we apply, that is first interior temperature it is 90 and second is exterior matting surface temperature is 60. And now next boundary condition is about related to the convection part. Okay. So here just insert you have to select these exterior surfaces initially, and that means these total surfaces. Now 32 surfaces faces are there, I think. So 24 faces are selected. Thirty, 31, 32. Okay, so you can see that total exterior surfaces are selected. Here why we have not selected these pieces, because here the bolts are inserted, we are inserting the bolts, so that's why we are not inserted selected that faces, right? Okay, so 32 faces, you can see that 32 faces are selected, right? And just I can go for right click and go for the convection, right? Okay, now in convection, okay, when we click on that convection, okay, then you have to see that the film coefficient, right? Okay, that is very important. It is stagnant air simplified, right? And that is stagnant air simplified. Yes. Okay, so be sure about that. just you can just import. Okay, and stagnant air simplify. Okay, and ambient temperature is, I think it is 20 degrees Celsius. Okay, so the ambient temperature will be 20 degrees Celsius. Then after that, solve the model for the temperature and heat flux. Okay, so let's say solve for what, temperature and total heat flux. These are the two, and you can say that solve this problem. Okay, now you can see that the temperature variation, right? The maximum temperature is how much in this? It is 90 degrees Celsius, right? And what about the minimum temperature? That is 60 degrees Celsius. Okay, you can see. Heat flux 0.77, right? That is watt per mm square. Okay, but these results are actually for polyethylene. We are trying to find out for what? These are the for aluminum alloy, right? Okay, so this is for aluminum alloy. It is here. You can see that point results are 0.7449, and 90 is the maximum, right? So here we are getting as a 0.77. It's okay. There will be all of you know that where the error is there, right? Actually, there will be error in the meshings, right? A number of nodes and elements will be different, right? So that's why you will get some variations in the results like that. So this is what for the aluminum alloy, right? Now let's same we will try to calculate for next, that is for the polyethylene, right? So this is a polyethylene material. Here we are selected. Okay, same steps are there, right? Just you have to select their material as a polyethylene, right? The next yeah, meshing, let's say 100 relevance, right? And just say that generate mesh. Then go for the applying the boundary conditions. So that is for interior surfaces. So total 13 surfaces are there in there, which are subjected to a temperature of 90 degrees Celsius. So that is applied. Then this surface is subjected to a temperature of 60 degrees Celsius. That is also applied. Then go for the convection boundary conditions. Okay, so 28 and how much? I think. Right. So these are the 32 phases. Okay, which are subjected to convection part, right? That is stagnant air of 20 degrees Celsius. So these are the boundary conditions we applied. Then we'll try to find out the temperature and total heat flux. So select that and just click on the solve. So now we can see that the total heat flux we are getting here as 0.0014739 for the polyethylene material, right? And for temperature we are getting as a distribution like this. Maximum will be 90 and minimum will be 49 point something like that. You will get the temperature results at any point here. Just you have to select the probe and just you have to click here. You can measure the temperature anywhere. In this case it will give the temperature actually because we are seeing the temperature, right? Same here, you'll get that red color indicates the temperature is 90 degrees, so that's why here it is showing like 60 degrees whatever we have given here, but here in intermediate temperature you'll get that. Okay, so like that. Same for maximum minimum also you can try to find out. Same for the heat flux results also, you can see that with the help of probes you can select with the max and minimum, also minimum and maximum heat flux. So this is for the polyethylene material, right? And the other one results, that means these results are for the aluminum material, right? So you can do the comparative study, right? Here for the temperatures and total heat flux of these two materials for a pump housing. Here you can see, right? Total heat flux we are getting for aluminum it is 0.77, but for the polyethylene we are getting it as an 0.001473 like that. Okay, so that is what difference. You can take a third material also, right, for structure steel or any other material, and you can rubber or cork, anything you can take, right, what you want, and just you can do the analysis for your practice purpose. So this is the analysis, right, or steady state thermal analysis of polyethylene and the aluminum pump housing casing, right?